Okay, thank you. Very happy to give these lectures. So I assume you have no prior knowledge of string theory, is that right? Or at least a few of you don't, many of you don't. Okay, so we'll see, today we'll see generalities of string theory and start with a hardcore. And in the morning, start a little bit more, and then the afternoon will be more hardcore bosonic string, and then we'll do the superstring, and hopefully strings. Maybe I will cut, so let's see how we do in time. Maybe I will cut a little bit of this, of heterotic string, for example, to get to dualities, which is very important. I'm mainly using the first book, String Theory and M Theory, from Cambridge. I should say this off the record, but I have the PDF if anyone wants. And well, there are other references there. And it will be Blackboard. Don't worry about the slides. It will be Blackboard. I just wanted to put the program there and some drawing, which is nice, and I'm very bad at drawing. So the first thing is I want to motivate why string theory. And sorry, my handwriting is horrible and it gets very small, but please tell me, I write at the same time as I say things, but if it's really too small or too incomprehensible, please ask. So you know very well, so we have four forces in nature, the electroweak force, the strong force, and the electroweak is I should say the weak force. An electromagnetic force. And these are forces, the forces that keep the atom together, the nucleus together. These are forces that are very important at the order of 10 to the minus, let's say, 15 meters, which is the scale of the atom. And these are very well described by quantum field theory. QFT, which this, I'm assuming everybody knows, some quantum field theory. And then on the other hand, at the very large scales, we have the gravitational force. I mean, when I mean as low scale, at small scales and large scales, what I mean is what's the force, what's the important scale of the force? Where is this force particularly important? And this is at the scale of the atoms and the nucleons, while gravitational force is the force that keeps us on the floor, and is a force that is very important at the scale of the solar system or the galaxy. So we can put some scale, which is 10 to the, whatever, 10, let's put some scale, 10 to the 12 meter, or from, let's say, from 1 meter to 10 to the 10, or even larger. But you see that there are 15 orders of magnitude between this and this. And this is very well described by general relativity, which I also assume you know. Now, if one tries to combine these two naively and do a quantum theory of gravity, so naive quantum gravity would be to start with the Einstein-Hilbert action and quantize it. So the Einstein-Hilbert action minus 2 over kappa square, square root of minus g, and the Ricci scalar. Minus g because we will use conventions in which the Minkowski metric is -1 in time and then 1. And usually, I mean, for this argument, we're in 4 dimensions, but okay, let me write it like this without. For this argument, that will be in 4 dimensions, but we will work in a general number of dimensions. And so for a time-like trajectory, this is negative. So you put this minus sign. And for a time-like trajectory, well, in general, this determinant is negative, so you put a minus sign. And so naively, so when you do quantum field theory, what you look at is the dimensions of the coupling constant, which is here k. So k is 8 pi g Newton to the 1/2. And if we look at the units of k, so first we'll use natural units. So you've seen natural units, I guess, right? So these are units where h bar and c are equal to 1. And that means there's only length and energy or mass, which is 1 over length. So as a scale, there's only a length scale, or the inverse, which is a mass scale. And if you look at in these natural units, this k has 1 over units of mass or energy. And this is a sign that is a non-renormalizable theory. That means when you add loops, the loops come with a given energy or momentum, and if you want to make things dimensionless, you will have to, so the powers of momentum will come upstairs, and that means the more energy you have, so the loops count more and more, the more, if you go in loops, you add powers of k, of the coupling constant, and then it will grow more and more with energy. So that's a sign that the theory is non-renormalizable. So this is a bit naive. This is first counting. Actually, GR without any matter, so here I wrote the Einstein-Hilbert action with no matter. It's better than, it's a bit better than this. It is renormalizable at 1 loop. That was shown by Toft and Bellman. And actually, it's a very nice and short explanation, but it works only at 1 loop and without matter. As soon as you add matter, and if you just want to go to more than 1 loop is not renormalizable. So then, a naive theory of quantum gravity doesn't work. But yes. In 4D, yeah. Yeah, sorry. Yes, that's what I said. For this argument that work in 4D, yeah. But no, yeah, right. Yeah, because you integrate, it's the integral over this that has to, yeah. But it gets worse in more dimensions, so that's not, yes. Yes.
When you say that one of is normalizable attributes with matter, you mean that like all the endpoint functions at one loop you just need a finite number of counters?
Yeah, you need a finite number of counter terms. Yeah, you can absorb all infinities in a redefinition of the for any endpoint. Yes. Yeah, so you can look at this. So, well, it's a paper of Toft and Bellman. It's very nice if you're interested and short. But. Okay, so now if we go back here, okay, we have 15 orders of magnitude or more in difference. Why do we care? I mean, it could be, not why do we care, but it could be why do these such different scales have to be described by the same theory? But if you say that, actually, the problem is, and here comes why I wanted to have. Okay. So you have this problem if you do that, which is the snake that bites its tail, because at the, this is a pointer, right? Does it work? No, never mind. Maybe one has to turn it on. Well, it doesn't seem to work. Anyway, because what happens at the smallest energy, like for example supersymmetry or axions that maybe you didn't see, but I guess you saw supersymmetry. It dictates. It's very important. Sorry, some things are in French, some things are in English. No, it's all in French. But matière noire is dark matter. In Italian, it's probably materia nera. No, how do you say? Oscura. Yeah, oscura. Okay, so dark matter, which is important at the very large scales. What makes dark matter? Well, one of the candidates are axion, supersymmetric particles. So what happens at the smallest scale is very important for what happens at the larger scales. So it's you really, you cannot really say that these are two different scales and one doesn't affect the other. Okay, so now what does one do? Well, now there are basically two ways of reasoning. So one is to say that, well, no, let me say something more. Let me give you a bit more motivation of why we need quantum gravity. So let's not string theory yet. Okay, that's better. Now, why quantum gravity? Because if you want to describe a black hole, so one motivation is that the scales actually go together. And in France, they really like les deux infinis, the infinitesimally small and the infinitesimally large, they go together. The two infinities is not such a popular expression elsewhere, but in France, there are institutes of the two infinities. And so if you want to describe black holes, for example, these are objects which are intrinsically, well, gravity is very strong at a very small scale. So it's not even two scales that go together, but this is gravity being strong at a small scale. Or if you want to understand the Big Bang singularity, or in general, space-time at the smallest at the smallest scales or smallest distances. You need a quantum theory of gravity for all this. And these are all sort of singularities. And to understand, so black holes, the Big Bang, space-time, and the smallest distances are all singularities that appear in general relativity. So again, instances where gravity is very strong at small scales. And then on the other hand, we have singularities in quantum field theory as well. So please interrupt, I might be going fast here, but please interrupt. So singularities in QFT, you've seen, are these renormalizations. So when you do perturbation theory and you go to the UV, you get a lot of infinities that you have to you get divergences in the Feynman diagrams. Feynman is 1n. That you remove by renormalizations, and you do remove. And this is something that you do order by order. And even though this gives results that make sense, are physical, and it works very, very well, it's horrible, right? Doing this, I don't know, when you learn quantum field theory, this is not nice, having these infinities that you regularize order by order. So what we string theories people believe is that the standard model is an effective theory that has to be UV completed. So this could say I didn't have to erase, there was the other blackboards. And when I say standard model, I mean completions as well. I mean, we already know that the standard model is not complete because of neutrino masses, because of dark matter. So when I say standard model, I mean completions of standard model, so beyond standard model, but as a quantum field theory. So this could say that standard model and its completions are an effective field theory. That has to be UV completed. or let me, because UV completed looks a little bit like this, but an effective theory that must come, let's say, must come from some UV, let's say, complete theory. So, and by complete, I don't mean these completions. Again, I'm not saying beyond standard model. I can leave that. So, what I mean is that that standard model and beyond are maybe effective theories. And actually, so these are singularities in QFT, and these are singularities in IR. And they might have the same origin at the end of the day. So, and GR. So might have the so in both, we're treating space-time as a continuous, and maybe that's a problem. Continue. So as a continuous differentiable manifold, as you in GR. And so that's more for GR. And in QFT, the particles we treat them as point particles. And those two things might break down at some scale, which is the typical scale of quantum gravity. So we expect something to happen at a scale, and let me continue here. So if I want to cook up a typical scale of quantum gravity, and forget about natural units, what constants do I have to use? I mean, quantum theory, h bar. And gravity, G Newton. Okay, so now I have these two objects. If I want to make something with dimensions of a scale, I have to divide by C and take the square root. And this is what's called L Planck. And this is 10 to the minus 35 meters. So it's 20 orders of magnitude smaller than the scale we talked about. If I come back to the to this. So it's so we talked about this, the scale of this is the scale of the atom, the scale of the nucleus. So it's we didn't even go there in that snake. So we really expect something to happen at this length. And maybe before, so okay, we'll see this. And if you want now, if we do natural units again, taking h bar equals c equals 1, we said that there are only scales of length or energy which are inverse. So if we do 1 over L Planck, so L Planck will be LP. This is M Planck. And this is, well, I mean, this is not exactly 10, it's 1.2. And this is 10 to the 19 GeV. So it's a huge scale, 10 to the 16 TeV. So if you know that LHC has 10 TeV, this is 10 to the 15 orders of magnitude larger than the LHC scale. So length scales are tiny. The typical scale of quantum gravity, it's tiny in terms of distance and it's huge in terms of energy. But at these scales, we really, H bar tells you that you cannot, so quantum mechanics tells you that you cannot tell the position and the momentum of a particle. And then, so at these scales, then space-time should not be a continuum anymore. But now there are two different let's say, attitudes that one can, or two different ways to think about the solution of this problem of quantum gravity. So one is to say, okay, we have Einstein gravity, it works very well. And maybe what doesn't work very well is to quantize it the way we can quantize it. Quantize it via perturbation theory, because we saw that the coupling constant has units of 1 over the mass, and that tells you that it's non-renormalizable. But why? Maybe I don't have to do perturbation theory. That's a bad way to go. Maybe one just have to quantize it non-perturbatively or just different. And so that's one, that quantum gravity is the quantization of Einstein gravity, but done differently. But differently, but done differently than usual QFT. by a perturbation theory. So maybe some non-perturbative quantization of gravity. And this will say that GR, and then suitably completed by the standard model in which quantization, perturbative quantization works well. But also, it's not clear what we quantize. We quantize the metric, the connection, loops. So, okay. We don't know how to quantize, but there is some way of quantizing it, and the problem is in the quantization. But here, so the CR suitably treated and completed by the standard model. This correctly describes the degrees of freedom up to also at the smallest scales. And this is what's done in canonical quantum gravity, or a little bit asymptotic safely. Loop quantum gravity, in which you quantize loops. Let me put the number 2 here. And the other very different approach is one of string theory that says that GR is only an effective theory of effective theory in the sense of low energy. So at large distances, so distances from the meter, or much less of, I don't know, 3, 4, 5 orders of magnitude, 10 to the minus 5 meters, let's say. But so that's large distances, which is arising from a more fundamental theory. And this more fundamental theory has degrees of freedom which are very different than those of GR or the standard model or quantum field theory in general. So are very different. And either and this is almost white. Okay. This is a point of view in string theory, where the degrees of freedom are strings and not point particles, but okay, we'll get to that slowly. But let me pause to see if there are questions on this basic. Are you motivated enough? Are you motivated? Yeah! No questions? Okay, good. So this was a warm-up. Okay. So string theory. Okay, so the main idea is we don't have point particles anymore, but we have strings, which can be closed. So this was point particles. And we have strings that can be closed or open. And we'll see, of course, the difference. And they have a typical scale that we call L string. L string is a typical size of a string. We don't know what it is because we haven't observed the strings. But so this can be, or let me put it this way. I don't know what a conservative estimate. Let's say, I don't know, 15 dB. Let me put, or if I put much less, then I can put 10 to the minus 20. I don't know, maybe 25 would be let me put this. I mean, I'm not 100% sure what are the scales that have been already ruled out experimentally. So maybe 25 is a bit on the, it's a bit on the large side. And it can be as small as the Planck scale, which is 10 to the minus 35. So it can be larger than the Planck scale, but it's small enough that we haven't observed it. And M string, which is the inverse, then it's smaller or equal than and Planck, which is 10 to the 19 GeV. So here I put 10 orders of magnitude, so 10 to the 9 GeV. So that's 10 to the 6 dB. I think that's safe. And something that we will use a lot is the square of this alpha prime, and we call that alpha prime. So by definition, alpha prime will appear a lot. This is L string square, and to be annoying, people put the factor of 1/2. I don't care too much about that 1/2. But this alpha prime that will appear all over is a square of the string scale. We'll talk about alpha prime going to 0, and alpha prime going to 0 is this going to 0, so it's like seeing the point particle limit of the string. So from now on, I will mostly write alpha prime instead of L string square. So we will have Feynman diagrams. I mean, the way we quantize strings is perturbative, but the point of Feynman diagrams is, so for example, in point particles you have something like this. I don't know, an electron with the electric field. Now this, well, depending on whether these are open or closed, suppose that these particles correspond to closed strings, then this is replaced by this diagram here. My drawings are... So two strings going into another string. This diagram, if you look at like this, is like a pair of pants. So this is called the pants diagram. And every Feynman diagram, now if you added this going into two particles, so this will be splitting into two strings. So every Feynman diagram that you knew, you can redraw in terms of strings. And you can compute it, and it gives a finite answer. So that's very nice. I guess we won't see that because there's a lot of things involved in doing this calculation, so it's harder than computing this, but there are no infinities for anything you put. And here there's already something that you can see. This point in space-time, where the Feynman diagram, where these things meet, now it gets sort of blurred here. I mean, not blurred, but it gets, how do you say? I mean, it's not, there's no singular point. So this is a smooth surface. It doesn't have any singular points in space-time. And this is very roughly why the infinities go away. No singular point or points. If you put two strings, this going to two strings, and there will be another singular point, and here there is no. So all these diagrams are finite. They are harder to compute, but you don't have to do any renormalization to get a finite result. Okay, and so to motivate you further, so we will see all this, but let me anticipate the nice features. So we will find gravity. What does it mean that we will find gravity? We'll find a massless spin to particle that interacts like the graviton in GR, and we will see all that. Yeah, we'll see. So massless spin to particle, which smells like the graviton, but it smells, it looks, and it is a graviton. It interacts as a graviton. We'll find gauge theories. Which means massless spin one particle and this corresponds also to non-abelian. So, I don't know, photons, gluons, I mean, can be abelian, non-abelian. We also have the matter, spin 1/2 particles. When we see the superstring. So we have supersymmetry. So consistently requires supersymmetry, though, I mean, I will mention that there are some non-supersymmetric strings, but they sort of start from, let me say supersymmetry. And some new feature, which is extra dimensions. Which is, so consistency requires so in the superstring, 10 dimensions, so 10 space-time dimensions. And you might think of this as something horrible, but it's actually it's a very nice feature. So for example, this something we'll probably not see. But depending on how we go in time, we'll see it or not, but let me say something basic. So what's the idea? So we see 3 + 1 dimensions. So the idea is that the 6 extra dimensions are small and we don't see. They are compact in some, they are curled up in some compact manifold, and that process we call a compactification. And the idea is, so for example, that if our universe is, if these are the 3 spatial dimensions of our universe, let me do it like that, is that at every point there's an extra space of 6 dimensions, so let me do 1 extra dimension. So there's a little circle at every, well, if this is not very clear, so let's say that this is This is space. The extended space, and so in 2 dimensions, and let's do 1 extra dimension. So the idea is that this is curled up in some small space. That we haven't observed, and again, that gives another possible scale, which is, in general, the way we know how to treat these extra dimensions is when this scale is much larger than the string scale, but that's not necessarily the case. Yeah, and hopefully we'll see this. But a very nice thing about this, and this was already, having a 5th dimension was already discussed in the 50s. So, and Kaluza and Klein, this is Kaluza-Klein in the 50s discuss what happens with general relativity in 5 dimensions. And one thing that they showed is that you have this off-diagonal component of the metric, G mu 5. So where mu goes, well, from 0 to 3, so this could be G mu 4 called G mu 5, G mu 4, but it's easier to understand to put G mu 5. So the off-diagonal components of the metric from the point of view of the space-time, this is like a vector, so this index here we don't see. And then what they showed is that diffeomorphisms in this 5th direction are like gauge transformations here. So this is some way of unifying GR and electromagnetism. At the level of a linear and classical theory. So I'm not saying otherwise, why bother with all this? We just put extra dimensions and everything works. No, this is just a linear one, I mean, at the linear level and classical theory, but this is very nice. And these extra dimensions also give a lot of richness to the theory, because depending on how these extra dimensions are curled up, depends on what happens, what do you see in space-time. We also see, let me put here, no free dimensionless parameters like the alpha in the standard model 1/134. This doesn't happen here. There is no free dimensionless parameter. And the ones which are dimension full, we cannot say they are free, because I mean, in principle, one can observe that, and that's fixed to be something. And the last very nice thing is uniqueness. So we will see in the class that there is, in the superstring, well, that there is a bosonic string, and then we'll see type 2A, type 2B, type 1, heterotic, 2 heterotic theories, and it looks like a big zoo, and you start, okay, then I don't believe it too much. But actually, these all theories that one sees are related by what's called dualities, and we'll get to that. So there's a single consistent theory of superstring theory that we can see in different regimes, and it seems to look different, but there's a unique theory. Okay, since you said you were motivated, by now you must be much more motivated. So questions about that before I start writing equations, I mean, more than this, actions and things like that, yes. Yeah, that's true. We have a Q&A session, that's good.
What's the relation? I can't quite see what's the relation between gravity and massless spin-two particles. Like, why does gravity tend to push us back?
Yeah, so this, I mean, if we want to see gravity like this as an interaction of gravitons, I mean, these are the carriers of the gravitational force. I mean, or to say it bad and simple, the metric has two indices, so it's a spin two objects. Its carrier, it's a quantum. Yeah, carries. What's that's a better word. The quanta, yeah, the quanta of this gravitational force should be a spin two particle, the same as the quanta of a force mediated by some gauge field, or it should be a spin one particle. And then there are, you also have scalar forces mediated by spin zero particles. Yeah. Other questions? I mean, it's true that we have the Q&A. And something about the Q&A, I have exercises if, yeah, I don't know how, Stefano, how does that work with the Q&A? Do people give? I mean, if you want to work during lunch, because I guess, or in the evening, I mean, I have exercises. You ask me if you want to do exercise. Sometimes it's when doing exercise. I mean, there are no exercises of this, but from what I'm going to say from now on, I have exercises, and if you want, and then you can also ask about that in the Q&A. But indeed, there are more, I mean, it's good to have that Q&A. That doesn't mean you shouldn't interrupt, because it's important. If I keep going and nobody's following, better ask during the lecture than afterwards. Any other question? Okay. So we'll start with the bosonic string. And the bosonic string, I will see, is not a good theory. And you'll see why. But still, is the basis of the superstring will build from the bosonic string, so any course starts from the bosonic string, and this won't be the exception. I mean, it would be silly to start complicating things when you just start from that. And so the motion of strings follows the principle of minimal action. And to see how it works, we can go back to the point particle, which you must have seen, but sometimes the word line, the word line sort of formulation is not so used, but for us, that's what we will use. So back to point particles, or let's say for point particles, let me draw here. So a point particle, when it moves, it draws what's called a whirl line. So it draws or it swipes. So let me draw it. So we have a point particle moving in space-time, in space. And this is the whirl line. We have some coordinates. I don't know. And I don't know, let me do into, I don't know, let's say this is x1, and this is x0. And this is x1, I don't know, x2, x3. Okay. This whirl line, I can express it as, for example, giving x. So xi as a function of x0, where I goes from 1 to d minus 1 here. So d is a number of space-time dimensions. And we leave it like that, general. So we say this is a particle moving in a d-dimensional space-time. So we could give so xi as a function of time, but this is not very covariant, right? It's not nice. So this breaks or hides, let's say, it's not breaks, but hides the covariance of the theory. So if this is moving in some curved space in particular, that's not a nice way to parameterize it. So what we do is to define a parameter along the whirl line that we call tau. And this could be, for example, tau equals 0, tau equals 1, tau equals 2. So this tau is a parameter along the whirl line. And what we do is give x mu of tau. So we parameterize the whirl line by giving all the mu. So mu goes now from 0 to d minus 1. So this tau equals, well, I put it here, but I don't know, that was this could be tau equals 0. It doesn't, tau equals 0 could correspond to t equals minus 1 in dimensionless units, right? X1 equals to whatever. So this So this tells me how the world line embeds in space-time. This coordinate x mu of tau. And if I want to see how this particle moves, now if I'm in a coarse space, so usually you are given the geodesic equation, but that geodesic equation can be, it follows from the principle of minimal action. So this particle will try to minimize the action, make the length of the world line as small as possible. So the action for a point particle is 0 and 0. I put 0 because it's a zero-dimensional object. So we'll do S1 for a string, and we will do in general SP for a p-dimensional object. So this action is minus m, this minus, this is an exercise, that this minus is there so that you get potential energy minus, sorry, kinetic energy minus potential energy. That's one of the exercises. And where ds is the proper, so ds square is, here we need to put, is the proper interval, and we need to put a mu, a minus sign, because of the conventions of eta being minus 1, 1, 1. So this minus sign is for time-like trajectory. So time-like trajectories will have d square larger than 0 with that minus sign. So this is minus m. So this integral is along the world line. And this is minus g mu nu. Now if I write this as x dot mu, so the derivative with respect to tau, the proper parameter. So this x dot mu, x dot nu, d tau. Now I integrate from tau from, I don't know, 0 to something, or minus infinity to infinity. This here will also write it at x dot square. So x dot square means this. X dot mu, x dot nu contracted with a metric. I mean, without the minus sign. And as an exercise, I'll send you, or send Stefano, and he'll send you the exercises if you want to. Just because, so there's an exercise. Which is 1.2, is to show that in the non-relativistic limit, this is the potential energy minus, sorry, the kinetic energy minus the potential energy, what it should be. So no relativistic limit, so the velocity is much less than c, or much less than 1 in natural units. Sorry, no, this is d tau, sorry, this is, yeah, sorry, yeah, indeed. Thank you. Thank you. Thank you. So now it's dx mu, d tau, and then d tau there, yeah. Or I can or if I put this, now if I say that x mu is a function of tau only, then yeah, what we get is this. Yeah, thank you. Yes.
When we say that by reducing the parameters, we are showing that the theory is covariant. What exactly do we mean, like explicitly?
I mean, so I was going to say that in the for the string. So it means that this is reparametrization invariant. So now I can choose this, or I can choose another tau tilde where, I don't know, this is tau tilde equals 1. Here I have tau tilde equals 2, which is much more. But this action will be the same. The equations of motion will be the same. So in that sense, this is reparametrization invariance. And reparametrizations are like diffeomorphisms on the worksheet. So changing this tau is like doing a diffeomorphism on the worksheet. Yeah, I'm going to write that explicitly, but for the string. But yeah, thank you. So these exercises show that in the non-relativistic limit, this action is the kinetic energy minus the potential energy. So that, I mean, this is standard GR, but I don't know, this square line is not so much used. So then, and this potential energy, I mean, it's just the mass of the particle. If you do that exercise, we'll see. And did the other lecturers go the 1 hour and 45 without break, or you used to have a break? Eh? You have a break? Okay. Okay, let me say one thing and then you'll have your break. And also for me. So the problem, so this is, okay, nice and physical and we understand it, but there are two problems of that, which is that square root, which makes it hard to quantize, and that it has a bad, if I have a massless particle, this action is 0 and I don't know what to do. So there are two problems. First, the square root, and then that's difficult to quantize. And then that it has a bad m equals 0 limit. So we'll do something which I'm sure you didn't see when in GR, because one doesn't quantize GR this way, which is to cure this by introducing an auxiliary field. Okay, 5 minutes. Yeah, that's a good break. So 17, we come back at 22. Okay, let's start. Okay. Well, yeah. Well, yeah. Thanks. This I'll. Okay. Yeah, at the beginning I started like this. I was really slow. Okay, thanks. I'll leave it here. Okay. Well, next time I will do the break a bit earlier in the class. Okay, so we said this action, it's, I mean, we understand it, and actually there's an exercise, no, an exercise, no, it's with a, it's after what I'm going to say, but we understand it, it's just the proper length, I mean, the length of the word line, but it has these two problems. So in order to cure those problems, one introduces an auxiliary field. Let me do it here. So introduce an auxiliary field that we will call E, and it's also a function of tau, but it's auxiliary, so it doesn't enter with the derivative. So, and we'll write this action as 0 tilde, which is 1/2 of the integral d tau, E inverse x dot square minus m square E. So E doesn't enter with derivatives, so and it's very easy to show that action. So if we do the derivative with respect to E, so we have 1/2 the integral d tau, so minus e to the minus 2 x dot square minus m square. And this should be equal to 0. Or, well, I should do the derivative of the Lagrangian without the integral. Okay, but this says that x dot square plus m square e square is equal to 0. So this E is a square root of minus x dot square divided by m square, which is fine. X dot square is negative for a time-like trajectory. And now if we put that here, then, so 1/2 integral of d tau so minus e to the minus 2 is minus m square over minus x dot square and x dot square minus m square. So here e to the minus, sorry, no, e is the, no, this is all right. And e to the minus 2. Yeah, this is an m. And there was an e, sorry, and I'm writing in the, and there's an e. So square root, so m is positive, and, sorry, square root of minus x dot square. Now, if we are careful with signs, so you can write this as a square root of minus x dot square, square root of minus x dot square, and you are careful with signs, what you get is 2 times the same thing. So this is equal to, so this. So here, sorry, here I'm doing a 0 tilde. I went back to a 0 tilde. So it's not there. So then this is equal to minus m square root d tau square root of minus x dot square, which is the action we started with. So by introducing this auxiliary field, I got rid of the square root. And now this has a good m equals 0 limit. It's just in the m equals 0 limit is equal to this. And there is an exercise to convince yourself. So I will send you the exercises so that you don't get bored while having lunch. Is to show the equation of motion from a 0 tilde is a geodesic equation. So the x double dot mu plus gamma mu rho nu x dot lambda. So the geodesic equation that you are used to. Okay, why did we go through this? Why? Because this is we'll do the same for strings. So strings, let's do an open string. When it moves in space-time, it swipes now a 2-dimensional surface, which is called the wear sheet. So instead of a wear line, now we have a wear sheet. And this wear sheet, let's do xi and x0.